Okay friends, now we have already discussed the total CRO, the cathode ray tube, the trigger circuit, the time based generator, the horizontal amplifier, the vertical amplifier and the delay line. Now what we will do is, we will take the basic principle of operation of a CRO and see how a lab CRO actually looks and what its functions are like. So what we have understood is that the electron beam gets generated by an indirectly heated cathode. The control grid controls the electron density within the electron beam. The anodes, pre-accelerating, focusing and final, accelerate the generated electrons towards the screen in a focused manner. The electron beam, which is the electronic stylus in our case, gets deflected as per the strengths of the electronic signal and the time base fed to the horizontal plates respectively. The deflected electron beam then strikes the phosphor coated screen to give out visible light using the concepts of physics including fluorescence and phosphorescence. Fluorescence gives us an idea about the amount of light being emitted, and phosphorescence tells us about the time till which the small pixel would glow after the signal has left that pixel. A typical CRO is shown over here and its controls are mapped onto it. We have the screen, we have two inputs in this CRO. This CRO is known as dual trace. Dual trace means it traces both the inputs one by one. We have the general controls, we have horizontal controls, we have vertical controls. We also have an extra facility of component testing available in this CRO. The next couple of slides would help us determine what their roles are in a CRO. First, the general controls or the front panel controls of a CRO. The general controls are the ones that help us get good quality waveform on the screen itself. They are, the first one is the on off switch. The on off switch, when depressed, switches on the electron beam. It is important to note that while using a CRO, this on off button should not be used very frequently. It should be switched on at the beginning of the class and switched off only when the class is over. That is because, this being a cathode ray tube based CRO, the electron beam cannot be switched on and switched off intermittently. If it is done, then the electron gun may suffer from fatigue and may get spoilt. What we can do in order to ensure that the phosphor screen does not burn up, we can keep the intensity of the CRO to a very low value. The power on off switch, the intensity control, the focus control, the trace rotation, scale and calibration are some of the facilities that come under general controls available on the front panel of the CRO. The intensity control ensures that the electron beam does not have a very high intensity. That is because, although it looks very attractive to the user to have a high intensity electron beam on the screen, but it generally ensures that the phosphor coating on the screen gets burnt up very fast. So intensity should be kept as low as possible in order to prolong the life of the CRO. Coupled with the intensity is the focus. As intensity of the electron beam gets increased or decreased, then the focus of the electron also has to be taken into consideration. At a high intensity, the electrons, high intensity means more and more electrons are being generated by the cathode and being sent to the screen. That ensures, although the beam is sharp, yet there is a drawback. Drawback is the repulsion between the electrons themselves. So hence one has to apply focus control, which is nothing but a voltage on the grid of the CRO to ensure that the electrons remain in the beam. There is the third option called the trace rotation controls. This is meant only for advanced users and service personnel. Sometimes when the CRO is shifted from one position to another position, then within the CRO the electron gun loses its matching grid, and the trace, instead of being formed at the center of the screen, shifts a bit to one side, to the top, to the bottom, or the other side. So for fine tuning of this, the trace rotation control is used. Certain CROs offer us the extra feature of scale illumination. Nowadays what happens is, all students, everyone has a mobile phone, so you can take pictures of the waveform that you see on the screen, but it is not possible to put that waveform in your answer scripts or your practical files. With practical files it is still possible, you can go out and bring a printout, but during examination you have to trace the waveform on a butter paper, also known as tracing paper, and while tracing the same using a pencil, you need to have the scale to be illuminated for calibration purposes, and hence the role of the scale illumination. There is a button, as you can see in the slide, that is known as a knob. It can be a button, it can be a knob, that is written, there is a word CAL written on top of it, and you have to always ensure that this CAL button is clicked in the right place to ensure that the waveform that you get to see is actually calibrated. What we do, we make our theoretical calculations and we need to obtain the experimental result on the CRO based on those calculations. If there is no calibration or there is a calibration mismatch within the CRO, then what happens is it does not give you the right result, and if you don't get the right result, your marks are deducted. So therefore, in order to ensure for proper representation of the output signal, the CAL button needs to be checked. So what happens is, how do we read the voltage on the CRO? As shown in the previous slide, we have a waveform and we can read the waveform. We can see what are the units. With this, we can see that the units on the waveform where the knob placement is there is 0.1 volt per division. So we find how many divisions. So we see that there are 4 complete squares on the screen plus 4 minor ticks. Hence the square wave waveform that you see has a height equal to 4 into 1 plus 4 divisions into 0.2, that is 4.8 divisions. Since the voltage per division knob is at 0.1, hence amplitude of the waveform would be read as 4.8 divisions into 0.1 volt per division, that is 0.48 volts. Typically, under calibration, the square wave that we can see on the CRO is 0.5 volt amplitude and 1 kilohertz frequency. So we can know that with getting 0.48 instead of 0.5, we can understand that there is a slight mismatch between calibration of the CRO and the signal being input. Okay. So, with this we finish the general controls under the front panel controls of CRO. Now, we move to horizontal controls. The horizontal controls on the front panel include facility for us to shift the electron beam to the left or right of the screen. The times per division knob is used to measure the frequency and time period of a signal. We all know that frequency is the reciprocal of the time period. So, we measure the time period and take its reciprocal to find the frequency. There is a facility in this CRO which says cross 5 mag in the horizontal control. Then this facility is provided so that we can look at more complex signals by magnifying them, but it is only magnification. So, under this X5 across 5 mag, if we look at a signal, then its time period would actually be 1/5 of what we are seeing. So, one has to be careful that if this button is depressed, X5 button is depressed, then our waveform is not exactly of the same time period, but rather it is being magnified 5 times. The trigger level knob generally is kept in the lock position, but sometimes due to matching problems means matching in the frequency of the input signal and the time based signal, sometimes we have to unlock this trigger level position so that we can see a stable waveform. We call this running away of the waveform for a waveform that does not stop in the screen and we cannot take a faithful output. Horizontal controls also have an XY switch, and when it is depressed, then out of the 2 input channels, one input channel can behave as the X while the other behaves as the Y. This is of great use during looking at the phase measurement using Lissajous figures. We run the CRO in the XY mode, wherein we have 2 different input signals which may have the same amplitude, but they have different phases. In order to find, there are 3 aspects in a signal. In 2 signals, we compare 3 aspects: amplitude, frequency and phase. For a singular signal, there is only amplitude and frequency. So, in order to know the phase difference between the 2 signals, we use this XY switch. So, we have completed the general and the horizontal controls of the CRO. Now, we move on to the third, that is the vertical controls. These are the vertical controls, and as you can see, we can look at 2 different waveforms on this CRO at the same time. And as the buttons in the center tell us, we can also add the 2 signals. We can look at only one signal at a time, or we can look at the alternate signal. We can add them up and see the result. Okay. So, in order to view the waveform, any input signal has to be fed to the Y plates of a CRO. In this case, we have 2 channels, channel 1 and channel 2. So, at a given point of time, we can see 2 different signals. Why 2 channels are important? That is because for faithful representation of any signal, we look at the input signal after it is fed to an electronic circuit, and we look at the output signal to look at the modifications being carried out by that circuit. So, hence in this case, we generally need at least 2 channels on a CRO. And why we can't use 2 different CROs? They can of course be used, but the timing calibration would be different on both the CROs. Hence, a singular CRO, a single CRO with 2 different channels is the best bet in our practical class. The time base would automatically latch onto the signal. There is no problem with time base, which would have been the case had we used two different CROs. And the dual mode of two different signals can simultaneously allow us to compare both the inputs. Again, the x5 and function that we have already discussed, and we also have the invert in one of the channels that is done in order to find out how the circuit under consideration has modified the signals so that the crest of one and the trough of other are out of sync by a particular phase. So, after this we come to the time base controls. The time base controls allow us to measure the time period and frequency of a signal. Reciprocal of time period is the frequency and vice versa. And during measurement using a CRO, the variable of time period needs to be locked at calibration position. And the trigger mode is to be kept at auto for the measurements. That is because triggering should be automatic. It allows us, or rather the CRO, to pick up the type of input that is being fed to the Y channels. Initially, CRO being inanimate does not know what kind of signal is being fed to its input. The trigger mode tells the CRO that we have some Y input and hence you need to generate sawtooth wave using the time base. The CRO would ask, what is the frequency of signal that I am going to display? What is the amplitude of the signal that I am going to display? Are there more than two signals that I need to display? So, all this information is processed by the trigger and fed to the time base, and only then do we see a very stable signal on the CRO screen. The time period, it is defined as the time between 2 points on a signal and is measured using the product of times per division value and the horizontal distance between them, that is on the x axis. So, what we do? We feed the signal, we choose AC from the AC ground DC switch, we adjust volts per division and times per division for optimal signal display on the screen. We lock the variable control to cal and then take the readings on the tracing paper or a camera phone as required. We keep one point as a reference in the horizontal position to make the second point intersect any vertical graduation line. We measure the distance between the 2 points. Time period is then calculated as horizontal distance, that is the number of divisions, into the times per division setting on the time base knob. Finally, the volts per division selector on the front panel. This is the typical volts per division selector control on the front panel of the CRO. As you can see the knobs and you can see the readings, then we use these knobs independently to get good displays on the screen. How to measure the voltage? First, AC DC level of a signal. We choose channel 1 or 2 of the CRO depending on which one you prefer, and feed the input signal to them, which goes directly to the Y plates. The delay line calls into play. It stops the signal till the time base prepares itself. We select the AC or DC from the AC ground DC switch. We adjust volts per division and times per division knobs for optimal signal setting. We lock the variable knob at calibration. For DC level measurement within a signal, we keep the switch first at GND in order to set the reference level, and then at DC. We measure the vertical distance between reference level to the point to be measured. The DC level is the vertical distance, that is divisions, into volts per division setting. Measurement of peak to peak voltage. We apply the input signal to one of the Y plates, again set AC ground DC to AC, adjust volts per division times per division for optimal display, and take the reading as vertical distance, that is number of divisions, into volts per division setting. Sometimes we use the add function to cancel out the effect of superimposed signals which are undesired component on the signal that we want to observe. So, with this we finish all the front panel controls of CRO. Component testing facility is provided on certain CROs, and they are used to measure and see the performance of electronic components like diodes, capacitor, resistors. Most of the CROs do not have this facility, only a certain high-end CROs have this. So, typically how exactly do you see a signal on a CRO? It has 3 or 4 types of connectors. First is known as the BNC to BNC, BNC to crocodile clips, then there are certain compensated BNC probes, and finally the component testing leads. BNC, as the name suggests, has been developed by Bayonet Neil Kunzelman. Neil Kunzelman was the person who developed it, and since it fixes onto the CRO in a fashion a bayonet is fixed, hence the name Bayonet Neil Kunzelman. It was first used in World War II, and typically it was also referred to as British Navy connector. So, I hope students, you must have liked this lecture and you get some knowledge. So, hands on remains, and you must go to the lab using this slides as a reference and start on with your practicals. Thank you so much.